What's up, everybody?
Back over here, if I write a function and call it SGN and it gets some value, all I have to do is say if value is greater than 0, return 1. Else, if value is less than 0, return -1. Else, return 0. So this is a sign function. It receives a value, and this is very long-winded. I'm sure you could come up with some clever, condensed shorthand way of writing this, but I'm being very explicit. Greater than 0, give me a 1. Less than 0, give me a -1, or else 0. This is actually going to kind of tell us what quadrant we're in that super ellipse. So we should now, we have the formula in here, we should now, instead we're not using this simplified version anymore, we're using this formula now, we should be able to get a nice super ellipse. So let me go back here, oops, and hit refresh. I see the regular old circle. That's good. So let's get a little crazy, and let's put like the number 4 in here and see what I get. You can see now I have a rounded rectangle, kind of almost. So let's make a slider for n. So I'm going to create a slider, and I'm going to say slider equals create slider. When you make a slider, you need 4 arguments. What is the minimum value? What is the maximum value? What is the starting value? And what is the increment? And what I'm going to do is in draw, I'm going to say n equals slider.value. So now, whenever I tweak that slider, I should be able to change the ellipse. So that's n equals 2, and you can see as I move the slider what I get. Ooh, now that was like really hard to see, but you can see as I move. So I'm getting all the different possible super ellipse shapes. Now I could also change A and B. Like for example, what if I make A 200 and B is 100? You can see that's just an ellipse now, and I get other kinds of shapes with that. So you can see this is the beginning of the super formula. It's just a super ellipse. I have a single angle. I have some weird sort of conversion that I need to do to get an x and y, and then I have a begin shape and end shape. So in the next video, what I'm going to do is instead of showing you how to do this with just, let me come back, how to do this with just this particular formula, the next formula I want to approach is how do I get all the x and y's that satisfy, I'm going to scroll up to this particular formula. So when I use this particular formula, which just has a lot more math in it, but essentially the code's going to be exactly the same, you're going to see how you can get all the variety of these different kinds of shapes. And then at some point, once we get to there, we should be able to then take this formula and move it into 3D to create volumes. So I actually have never done this part before. I've done the super ellipse and the 2D super shape, and that'll come in the next video, which I'll release at some point from now, and then we'll move into 3D. So I hope you enjoyed watching this super ellipse video. Give it a try. Try adding some colors in it. Can you make a super rainbow? I don't know what that would be. Try making that and see what you get. What other kind of interactive features can you do? What kind of questions do you have about the math? And let me know how that goes. Thanks for watching. Welcome to a video tutorial about programming something called the super shape. Look at the formula. I'm going to do this in JavaScript. I'm going to use the P5JS formula. This is a topic which is a continuation of a previous video that I made about the super ellipse. I'm essentially going to use the exact same code I had in my previous super ellipse video and turn it into this other more elaborate formula called the super shape. The super shape this is Paul Bork's website. I'll include a link to it in the description. This is a page documenting how to do this from 2002, and the equation is something based on Johann Gillies. I'm not sure if I pronounced that correctly. And these are formulas that are designed to try to simulate and create different kinds of natural forms. And eventually, if I am strong enough, if I'm courageous enough, if I can manage it, I'm going to, in the next video, finally look at the super shape in 3D, which will allow us to start creating forms that look like this sort of stuff. But at first, we just want to see if we can make these 2D-like forms with different parameters for this particular formula. So let me come back, and here is the formula. Okay, so what's the core idea here? Let me come back to the whiteboard here for a second. The core idea, if you've forgotten, is that I have this idea of a polar coordinate system. So I have some r and some angle. And actually, what I'm going to do is I'm going to iterate over every possible angle from 0 all the way to 2 pi. And actually, you can generate interesting super shapes by doing this multiple times. So going like from 0 to 2 pi like 6 times. And what I'm going to do is with this angle, I need some way of calculating r. So that, for example, if one of the super shapes might look something like a flower, that r is changing based on the angle in a way like it's oscillating. Almost like you could just sort of do this with a sine wave. Like you could say, r equals sine of the angle, which is actually giving me like a backwards headache because there's so much wrapped up. But anyway, you get the idea. I need to calculate r from theta. And in fact, that's what this formula is doing. It's saying 1 over r equals all of this stuff, and phi being the angle. I'm saying theta, I think that's the Greek letter phi or phi, or I don't know. Everything's going wrong today. And, I can flip this. 1 over r equals that, so r equals that. So I need to figure out a way of getting this formula in my code. It's going to be a bit awkward. I'm sure I'm going to make some mistakes. But the other thing that's really important here is that looking deeper into this formula, there are 4 constants. Oh, a and b, by the way. Okay, so there are actually more than 4 constants. There's like 6, I think. There's A, B, M. That's not 6. Yeah, it is. A, B, M, N1, N2, and N3. So based on those values, you are going to get a variety of different results. And you can see here, if I look at this page, you can see with different values of M, we get these different results. So hopefully, I'm going to do this correctly, and we'll see the results that are on this page. So let's go to the code, and this is actually just the code now that I picked up from the super ellipse. And you can see I'm running this here. This is the super ellipse, which is just changing one particular parameter to create these different kinds of ellipsoid patterns. And I'm now going to go over here. I actually don't need this particular function, and I'm going to the thing that I'm going to leave in here, which is the most important thing, is this. So ultimately what I need is begin shape, end shape, every single angle, and I need to get an x and a y, and I need to draw that vertex. So this I need, and then I'm not going to worry about the slider thing right now. We'll come back to that later. What I also need is I need to have a bunch of constants. So I'm going to say I have n1, I'm going to have n2, I'm going to have n3, I'm going to have m, and I'm going to have a, and I'm going to have b. Now for simplicity right now, let's make everything 1. And obviously, you can declare and initialize variables all in one line in all sorts of fancy ways. But I'm just going to be very explicit about it. Those are all of my constants. So I need to go back and forth. I need 2 screens, really, because I really need to refer to this formula quite a bit. But I think what might make things nice, and actually, Paul Bork has code for doing this here, and I guess I could check it if I get confused or something wrong. But what I think would be useful to do is to create a function. I'm going to do that up here. And I'm going to create a function called super shape, and it gets an angle. So this function receives an angle. Maybe I should call it theta, A for angle, it doesn't matter. So it receives an angle, and it needs to return back r, because that's what I'm trying to calculate. So at the end, I want to return r. So let's see somehow, and I want to say var r equals 1. So let's just say right now, let's say this is my function. And then what I want to do here in this code is I want to say var r equals super shape of that angle. And then I need to say x equals what? R times cosine of that angle. Y equals r times sine of that angle. And if I wanted to, I could also scale these up by some arbitrary value. And I'm going to make that a separate variable, like radius, just to scale them up. And I could probably build that. I'm doing something ridiculous right now, but I'll fix this later because it's returning 1. So the idea here is I should just see a circle. I'm swirling in the strawberry. Oh, don't you wanna take a ride on a tic-tac? Download the Domino's app today and become a piece of the Pi Rewards member to earn points toward free pizza. Okay, great. So this is working. The idea here is that I have a function that takes the angle and sends back a value, and then when it sends back that value, I do it for every angle, and I get this circle. Now, of course, I'm getting a perfect circle because no matter what the angle comes in, I'm just returning 1. And now what I need to do is I need to get that super shaped formula in here. So let's try to do that together, and hopefully we get something that looks about right. So I'm going to go back to Paul Borg's site one more time. So there's a bunch of things I need to calculate. One is 1 divided by a times cosine of m divided by 4 times theta. Oof, am I really going to be able to remember this? I'm going to call this, I need some, I'll call this part 1. I did something terrible. So there's a constant called a. So this I don't want. I want this to be called. I'll call this theta. So 1 divided by theta times cosine of m divided by 4 times that angle. That's not theta. That's 1 divided by a times cosine of theta, which is the angle, times m divided by 4. Okay, so that's this thing in here. So then I need to take the absolute value of that. And then I need to raise it to an exponent, which is n2, which is to the n2th power. That's part 1. Now I need to do part 2, which will probably be somewhat similar. Part 2 is 1 divided by b times sine of the same thing to the n3 power. Okay, so what did I say? 1 divided by b and sine, those are the only things that change. And then this obviously needs to be part 2. Part 2, this is n3. Part 2, part 2. Okay, so now I've got that formula there in 2 different parts. By the way, this I think is a useful thing to do. You got this big elaborate formula rather than to try to write it all out in 1 line of code. So divide it into parts. Okay, so we got that. Now let's see. Okay, now I need to add them together. So I'll say part 3 equals part 1 plus part 2. Then I need to take the square root of it. So I can probably do that just in this line of code. Square root, right? And then I need to multiply it by n1. So I just need to say n1 times that. So that's that. So that, and this should be part 3 with no space. So this is mostly like me just like getting that formula in here. Okay, I think we're pretty good shape. I think I'm doing this right. Please. Now what else? Ooh, 1 divided by r equals all of this. So if 1 divided by r equals all of this, r should equal 1 divided by all of this, right? I can just flip that. So I should be able to say, and actually I don't need this bar r equals. I should just be able to say return, there's a dangerous thing that could happen here. Return 1 divided by part 3. Now I'm a little bit afraid of a divide by 0 problem. So I think I better put something in here like if part 3 equals 0, then return 0. I don't know if that's correct. We'll look in. And wait, this is not n times. Wasn't there something? No, that is. Yeah, maybe this is right. Okay, so I think I got this right, and maybe there's something else that I did slightly wrong. But let's see if this is good enough. I have a working version of this. I can always check it if this doesn't seem to work right. Okay, here we go. So let's just see what happens now if I actually let this be and let this go. Oh, and by the way, I had this like radius thing equal to 100. I don't need a separate variable. Okay, so let's now run this. Ooh, look at that. That's promising. So I got something that looks right, but it's a slightly different shape. So let's actually go in. Let's go to Paul Borg's page, and how do I get over here? Let's look at an example with n1 equals n2 equals n3. Oh, if m is 0, I should get a circle. Let's at least test that. So let me make m equals 0. Perfect. I got a circle. So I think I did the code correctly. So now if I go back here and I look at with all these equal to 1, but if I have m equal to 5, I should get that shape. So let me change m equal to 5 and run it again. Close. Do I have something wrong? It looks a little bit different. That's a little distressing. Pause. Back now, I figured out the error. So I had a major error, actually. I completely read the formula incorrectly. This is not the square root of all of this times n1. This is the way that this is written means it's the n1th root of all of that added together. In other words, if n1 is equal to 2, then it's the square root. So I really need to fix that in my code. So let me do that briefly, really quickly. So instead of n1 times the square root, I want to use the power function. Power takes something, and if this is like to the n1th power, part 1 plus part 2 to the n1th power, if I say 1 divided by n1 here, this is part 1 plus, this is the n1th root of part 1 plus part 2. So I can do that, and then if I do it again, we can see, aha, now I have the correct shape. But you'll notice something, look at this. There's like a weird mistake here, and you can see it doesn't look exactly right here. So one thing I've done very not carefully, and let me fix that here, is that I just decided in my loop down here to just say, let me look at every single angle. Start at 0, go to 2 pi, go up by 0.1. Well, that's not very thoughtful, because 2 pi isn't necessarily perfectly divisible by 0.1, and it's not that many points. I could say 0.01, and I'm going to increase the resolution of what I'm drawing much more. You can see now it looks much more like that super shape, but I probably would make sense for me to be a bit more thoughtful of it, and say something like, I want to have a total of 500 points, and then I want to have the increment, the angle increment, to be 2 pi divided by that total, and then I'm going to always go up by that increment. So if I just do it that way, then I can say this is 500 points. That's what I get with 500 points. And I could say something like, oh, whoops, I only want 10 points. And if you see that, you're going to see it still looks right, but there's only actually 10 points in there, and there's much less curvature because it's drawing big straight lines between some of those points. But this is, I think, a better way of being able to control this. With 100 points, it looks like this. So, how many points do I really need to get kind of like a good resolution on that shape? And when I do this in 3D, we'll need some sort of mesh. I hope I can do it in 3D. Okay, so let's look at this now. Now I have this slider down here. Let's at least do something like tie that slider to a particular value. So, for example, what if I were to say, so one thing I want to do here is, one thing that's interesting is that I want actually the increment values of m to be incrementing by 1. So I want to start with an m of 5, and I want to go between 0 and 10. And then what I want to do here in the draw loop is just say m equals slider.value. So we can just sort of make sure things are, dot value. Make sure things are kind of working. You can see now, you can see as I move the slider, that shape is changing, and we're getting exactly what is written or depicted on this Paul Borg website. So you can see m is 4, I should get that, m is 5 is that. Now we can see, okay, what are these shapes here? What if I have n1 equals n2 equals n3 equals 0.3? Now I could change all of these, and obviously I could be much smarter about not having 3 separate variables if they're all the same value. And now we can see, what does this look like? You can see now I have this particular kind of shape, and you can see what it's doing as I change that value of m. So I'm going to stop here, because I could continue doing this forever. I could say, well, let's make sliders for all the different variables. Let's try all of these different possibilities. Let's see, can we get all of these different shapes? So this is what I would encourage you to do. And by the way, you don't have to tie them to sliders. Try tying those variables to like a sine function. I could do that really, really quickly right now. Like, for example, if I have, I'm going to have a variable called oscillate equals 0, and I'm going to say m equals, map sine of oscillate, which goes between -1 and 1, to some value between 0 and 10, and then I'm going to say oscillate goes up by 0.1, and I'm going to refresh this. You can see now this is happening. That's happening very quickly, but automatically. So let's make it go up much more slowly. And you can see here what's happening is it's kind of like changing that value on the fly, and the shape is kind of like wrapping around itself, unfurling and furling. So there's a lot of possibilities here. I could add HSB and make it a rainbow, but I encourage you to explore this, play around with it, see what types of forms you can get. And eventually, at some point, I will get to that next video and try to do this in 3D to get a lot more elaborate forms. Okay, thanks for watching this particular video, and I look forward to seeing you in another one in the future. Bye-bye.
Still, no one wants to get it. Wait a minute, I don't mind. No one believes that. The $7.
Hello and welcome to another coding challenge. In this coding challenge, I'm going to program a visualization that looks just like this. That was for the thumbnail. And I'm going to do it in P5.js using JavaScript in the browser. What's running over here is an example that I made previously in processing, which will give you higher performance. So at the end of this video, perhaps I'll take a look at that very briefly. So I'm not going to start from scratch. This video is really going to be built on top of this idea of two-dimensional Perlin noise. If two-dimensional Perlin noise is not familiar to you, stop now, go to the video description, and go and find my series about Perlin noise, and then come back. Okay, hi, you're back. Great. Okay, let's get started. So I'm going to start from this particular piece of code, which generates this particular output. So this is already an example with two-dimensional Perlin noise, and each pixel gets a grayscale value according to two-dimensional Perlin noise. But I want to do something different. What I want to do is, in the kind of grid of pixels, right? This is my
big ass
resolution grid of pixels. Instead of having a grayscale value for
this strawberry, bro. It's like a baseball, bro. They're pretty big, bro.
each pixel, so to speak, what I want to have is a vector. I want to have an arrow pointing in some direction, and I want that direction to be a direction set according to Perlin noise. Because ultimately, what I'm going to do is I'm just going to like pour a whole lot of particles into this area, which is known as a flow field. This is known as a flow field, and I pour the particles in, and they're going to follow the arrows. And we'll see what happens. Okay, so the first thing that I need to do is start revising the code to make vectors instead of pixels. So let's take a look at how that might work. So I'm going to work with a very low resolution canvas, just 200 by 200, just to kind of get things kind of started here. And one thing that I also need to think about as a core variable here is I need to think about what is the ratio of kind of cell to width. So I don't want to have an arrow for every pixel. It's going to be unreasonable for me to have 200 vectors. Instead, maybe I want a vector every 10 pixels or every 20 pixels. So let's make that a variable called like scale. I'm going to call it SCL, short for scale, and I'm going to say that's 20. And then what I also need to have is columns and rows. So I'm going to have the columns is going to be the width divided by scale, and I better floor that. Floor is something that gets rid of the decimal place, and I'm going to say rows is height divided by scale. So now what I want to do is I'm not dealing with pixels anymore. So I can get rid of load pixels, I can get rid of update pixels, and in fact, I can get rid of all this pixel array stuff. But let's just see that things are working.
I thought it wasn't going to be good because
it's
such a big strawberry.
Now go through all of the rows, and have X go through all of the columns. And what I want to do is I'm going to draw a rectangle. I'm going to draw a rectangle at X times scale. I got to scale up. Y times scale, and the size of that rectangle is scale. And I'm just going to give it a random fill for right now. And I want to see that I'm at least getting a grid of rectangles. So if I run this, okay, so this is working. So this is now going to be my grid. Now, what I've done is I put a grayscale value, a random grayscale value in every cell. Hey, why don't we make that a random noise value just